That was a great presentation, Allegra. Thanks for teaching us about packed files. I'm going to dig into databases in the microservices world. So a little bit different. Here's the part where I tell you, I am definitely going to post the slides on my site tonight. I've been that attendee trying to chase the speaker for their slide deck, and it's never worked out well, which is why you can go to robrich.org right now and click on presentations up here at the top and land on databases in the microservices world at the DevOps Lisbon meetup. The slides are online right now, and I put them in chat just in case as well. So while you're here on robrich.org, let's click on About Me and see some of the things that I've done recently. I'm a Cyril developer advocate. I'm a Microsoft MVP, a Docker captain, a friend of Redgate. And AZ GiveCamp is really cool. AZ GiveCamp brings volunteer developers together with charities to build free software. We start building software Friday after work. Sunday afternoon, we deliver that completed software to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp. Or if you'd like a GiveCamp here in Lisbon or wherever you're connecting from, hit me up on email or on Twitter, and let's get a GiveCamp in your neighborhood too. Some of the other things that I've done, SQL source control basics. Mine is chapter 8. That was fun. And I replied to a .NET Rocks podcast episode. They read my comment on the air and they sent me a mug. Woohoo! So there's my claim to fame, my coveted .NET Rocks mug. So let's dig into databases in the microservices world. We talked about this guy. Let's first look at application architecture. We started with spaghetti. We moved to lasagna. We're now in ravioli mode. I love this analogy because it kind of talks to the way that we did this. We started out with a big ball of soup. We moved to an N-tier architecture, and now we're in microservices where we have lots of replaceable pieces. Or said differently, we started out with a monolith on the left, and we moved towards microservices on the right. Now, a monolith was great back in the day. We created this monolith because it was difficult to deploy, and we wanted to get to a point where we could deploy quickly. We moved to microservices once we had containers, and now we can deploy lots of pieces really quickly. But one of the things is microservices own their own data, and that's a real core principle of a microservice. It does one small job. It's easy to replace. We can scale it independently of others. We can easily deploy this to replace content that may have failed or needs to work differently. And it owns its own data. A microservice should own its own data because now we don't need to communicate between teams. Hey, are you using this column? Should I obsolete this row? All of that is managed in that microservice. And so if the microservice no longer uses that data is no longer important and it can be deleted. But usually when we start talking about microservices, we end up in something like this. Yeah, we refactored our application into microservices. That was great, but we're still using one big monolithic database. So why do we end up here? Well, we end up here because the DBA said no. Well, the DBA said no because the DBA's job is to ensure customer success by ensuring database stability. By comparison, an applications app developers task is to ensure customer success by delivering new features. You notice something interesting there? Our jobs are both to deliver customer value. We just deliver it in different ways. So if we stand on the same side of that problem, our job is to deliver customer success, then we can focus on doing that and get past the DBA said no. Well, why did the DBA say no? Well, probably because deploying databases is hard. It takes a lot to be able to spin up a new database, and keeping that safe and secure is important. So we need some automation to be able to get our database automatically enrolled in backup and authentication. Have you ever been in that spot where you have a microservice that owns its own database and maybe it didn't get enrolled in backup? So I see that some data got corrupted. Let's refresh from backup. We backed it up, right? Right? That's an uncomfortable conversation. If we can get enough automation to get to the point where we can deploy these databases, provision these databases and automatically enroll them in backup and authentication, then we can get to the point where we can have lots of microservice databases. If we can't get to the point where we have microservice databases, then we'll probably want to use a bounded context. Now, this is a great in-between mechanism to get us close to microservices. A bounded context is a wrapper around that portion of the database that applies to a particular set of tasks, perhaps to a particular microservice. Now, as we look at bounded context, let's look at two examples, a shopping cart and a fulfillment service. The shopping cart needs access to a read-only view of the product catalog. It needs the broad descriptions. It needs all of the product images, and it needs to be able to create orders. That's the bounded context for a shopping cart. By comparison, the fulfillment center doesn't need access to the product catalog very much at all. Really, all it needs is the product ID. It needs to be able to update quantities on hand, and it needs to be able to mark the order as delivered or as shipped. A fulfillment center and a shopping cart have very different bounded contexts. And we can draw these bounded contexts to try to start imagining how our database needs to be split up into lots of little pieces. At the point where we get to automation around backup and authentication, we can get to what I'm going to call micro databases. A micro database is that portion of the data store that is allocated to a particular microservice. So a microservice may have one or more micro databases, but that micro database will only apply to one microservice. Now, micro databases are really elegant. It's an elegant way to get to that point. If we have automation around authentication and backup, and we can provision these easily, we can provision lots of different micro databases. A micro database is owned by one microservice, and other services need to call this microservice to get at its data. Well, what are some of the problems that we might hit here? Well, how do we do joins across different micro databases? Now, that's an interesting dilemma. If I'm, for example, running a month-end report, how do I get access across all of these things? Do I need to call the customer microservice in a loop every time I need to get that customer's orders? Then do I need to call the order microservice in a loop to get all of the details associated with this? I just want to run the month-end report. Instead, let's create an event sourcing system, an event bus, where each microservice can publish the content to that event bus. And those services that need to listen can listen to that event bus and pull in the details that they need. When it comes time to run the month-end report, we already have all the data that we need. We don't need to reach out into those other services because we've been able to siphon off the orders as they come in. So we eliminate joins with event sourcing. Well, how do we eliminate this contention? Who owns the customer record? Now, the customer record is kind of important. All of these different business units need to be able to use this. The shopping cart, the billing, human resources. Yeah, human resources loves to have secrets. How about sales? They're probably the ones that create the customers. But there's a difference between a lead or a prospect and a customer. A lead or a prospect may just be a phone number on the back of a napkin. A customer needs to have a reliable shipping address. So who owns the customer record? What if we create a new microservice that is the customer microservice, and it has a micro database, and it is two columns, one for the primary key and one for the account number, and nothing else. Everything else can be stored in a customer profile associated with that other service. So a shopping cart may have a customer profile including shipping addresses. The billing system may have a customer profile that includes credit card details. Human resources can have their customer profile with all of the secrets that they need. And sales, when they create a new customer, when they're ready to promote a lead to a customer, they can call into that customer microservice and say, I've got a new account number. Can you give me a new primary key? We've been able to eliminate the overlap between these bounded contexts, between these micro databases, by creating a new service whose sole purpose is to be able to facilitate that communication. And then each system that needs it can create a customer profile that has a foreign key back to this shared data store. So we've gotten to micro databases. We have enough automation to be able to pull this into place, and each microservice owns its own data store. That's great. Now, one of the things that's kind of interesting here is as we look at these microservices owning their own data stores, these data stores, well, they don't all have to be the same type. We can use different data stores, maybe even by different vendors, that facilitate the task best suited for that particular microservice. Now, microservice may need multiple data stores, or maybe they don't need any data stores at all, but they can provision the data store specific to their specific problem set. So let's take a look at, I love this quote. It was made by me right now. So the data stores don't all have to be the same type. Let's take a look at the types of data stores, kind of look at the pros and cons associated with that, and identify which data stores might be best suited to which problems. So there's a lot of different types of data stores. We may not get to all of them, but what's really cool is I hope to be able to impress upon you that you can choose a different data store than the monolithic data store that you've got, if you have enough automation to make this happen. For each of them, we'll look at the characteristics, pros and cons, best use cases, and examples. So first up, relational data. Now this one we know very well. It's rows and columns. We can think of this as an Excel spreadsheet. What's elegant here is that we have the SQL syntax that has been tuned for generations to make queries really fast. Now, part of relational databases is ACID compliance. Let's double click in on that. ACID compliance means that all of the content will either succeed or fail. We won't get a partial transaction. By comparison, we can look at eventual consistency. With eventual consistency, we could think of this like placing an order on Amazon or ordering a coffee at Starbucks. Now, if we go to Starbucks, we'll get from Starbucks a token, a ticket. They'll ask our name. And then they'll go do all of the steps associated with producing the thing. And when it's done, they'll call us back. With a similar mechanism, I can swipe my credit card to pay for this purchase. Now, if I go check my account balance right now, I may not have a charge on there, but by the end of the month, my bill will be eventually consistent and I'll see that charge in place. Eventual consistency means that if I write and then right away read, I may get the old data. Now that's okay. Compare that with ACID compliance. And we know that at the moment that we write, we will be able to get that new data. Relational databases focus on that ACID compliance, making sure that we get the data right away. Now, on the upside, relational databases offer a strong schema, this query syntax that is really elegant, and very optimized join and selection syntax. On the downside, it has a strong relation, and so we may need an ORM or a migration system to be able to adjust the database over time. SQL databases were also designed before we could really take advantage of multiple CPUs. So, pardon me, most SQL databases are not horizontally scalable. We just keep having to buy a bigger and bigger box. So here's some example SQL databases. SQL is a good default. Probably if you have a monolithic database, it is a SQL database. Next up, let's look at a document database. Now, sometimes we refer to this as NoSQL, but technically anything that isn't that relational database is NoSQL. So we'll specifically call it document database. In a document database, we have these JSON documents. We might store them as binary, but we have these JSON documents. Now, each JSON document could include nested fields. It could include different fields than the fields around it. Now, that's awesome. As we read by ID, we can grab the entire document and we can be able to take action. On the upside, we now are able to nest our structure. We can include related data in one spot. On the downside, our database no longer has a schema. So our application probably assumes how this database behaves, and it may need to make corrective assumptions. What if we try to where on a field that doesn't exist? What if we receive data that doesn't match the format that we're looking for? How do we handle that gracefully? A document database needs to handle this. So here's some example document databases. They're great because they're optimized for reads. If we have, for example, a product catalog or a news site or a CMS, we can go grab the article by ID or by slug. We can read the entire article together, the title, the content, the author name, the author's picture, maybe the first page of comments. We get all of that in one read, and our news site will work really quickly. Next up, let's take a look at graph databases. Now, what makes graph databases interesting is we have not only nodes, but we have relationships between nodes. So I can have a thing and I can have directional relationships to friends or friends of friends. And we have this really elegant syntax for querying it that allows us to traverse the relationships. So how is this different from foreign keys? It's that query syntax. With a graph database, we're optimizing for those relationships. So that is great, but we're also not optimizing for other things. So joins between unrelated tables is probably more difficult in a graph database. Here's some examples of graph databases. It's great for messaging apps, social networks, recommendation engines, places where you need that relationship between things. Next up, key value databases. Now, the beauty of a key value database is that we have a key and we have a big binary blob or maybe text blob of content. The values don't need to have the same structure. What's great about this is we can store things like configuration and shopping cart details, anything, session details, anything that we need to store that might be different across different users. And as we read that particular key, we can deserialize it with whatever mechanism makes sense. On the upside, anything that happens by key is really easy. On the downside, we can't create queries that look at any other types of data. If we want to where on another field in this data store, we need to basically loop through the entire data store, deserialize it using whatever technique we need, and then look at that particular content and do a subsequent query. So it's great for caching and configuration user session data. Here's some examples. Next up, time series databases. What's interesting about a time series database is with traditional relational tables, we end up with rows and columns, and in each cell is exactly one value. With a time series data, we can create time buckets. So the columns represent a particular time window. Now we have multiple values in each cell. So we can do things like average, max, min. We can compensate for missing data. Time series databases are great for building candlestick charts. Anything that's really focused on event and date. On the upside, windowing functions allow us to normalize the data for unusual events. On the downside, it's not great at other things. Here's some example of time series databases. It's great if we're processing very specifically time-centric data. So mobile devices, sensors, stock trades, things that are very time-centric might work really well in a time series database. Next up, text search databases. Now, the beauty of a text search database is that we can find content within a particular document or find documents that match this phrase. We might choose to pair this with a natural language processing system, and now we have a search engine. Text search databases aren't a search engine, but paired together, we can invent a search engine. Text search databases use an inverted index. We can think of this like the index at the back of a book. We can go through that index, we can find the word that we need, and it will show us the page number where that word exists inside the book. Now that's great. If we're trying to index text, if we're trying to find which documents match this phrase or where in this document we have this phrase, then that works out really well. On the downside, we can't really filter by anything else. So if we want to find books of a particular genre, or if we want to find other documents based on a particular criteria, then we probably need another database to be able to store that metadata. We'll first query that other database. Maybe that's a NoSQL or a SQL database. And based on the matches there, now we'll query our text search database to see if our phrase is in this document. Another downside to text search databases is stop words. A, and, the. These are words that don't have a whole lot of semantic meaning in English. So we might choose to remove these from our inverted index just to make the index smaller. If we're working on roads, we might remove av and road and street from our inverted index because these things have no meaning. Well, what about Avenue A? Does that mean that Avenue A is completely unfindable within our text search database? Stop words are very culture and language specific, so tuning stop words can be difficult. Here's some examples of text search databases. It's great for finding keywords in a document or finding documents that match a phrase. But we may need to create another data store to be able to keep the relation to match other data, such as a relational database, to pre-filter our documents. Next up, object stores. We can think of S3 as a great example here. Now we have a key, And we can pretend that a key is a path and pretend that it's a file system, but really that key is a unique index, kind of a key value store where the value is a big blob. Now, this is great for storing very big things, database backups, video files, maybe large log files. On the upside, we can now query by ID and be able to get at that big blob. On the downside, we can't really filter by anything else. If we ask the question of our object blob store that stores database backups, when's the last time this file was modified? Well, we would have to deserialize each object in the store to say, hey, do you have a new version? Do you have a new version? We're untarring each one. We probably want to keep metadata like that in another database that we can query. And once we find the correct backup file, we can go grab that from the object store and untar it. Object stores. S3 is the great example, but we have other object stores, and we could even use a file system to represent an object store. It's great for storing big things, but we may want to pair it with another database system that keeps metadata. Next, event sourcing. Now, we talked about how event sourcing can help us with joins. With event sourcing, we can communicate asynchronously between systems. The producer can write data to the end of the event store whenever it's ready, and the consumer can pick up and continue on. So, for example, I have a producer that's writing version 9 in place right here, another consumer that's reading version 8, and another consumer that's a little bit behind, it's reading version 6. Now, it's wonderful because the producer doesn't need to call into the function. The consumer doesn't have to be online. They can now communicate asynchronously. We can choose to subscribe to particular channels or topics to avoid noise that we don't need. And if at any time the business logic changes, we can start back at the beginning and reread all of the changes with our different business rules. On the upside, it's great to be able to keep track of changes to communicate asynchronously between these services. On the downside, it is a very eventually consistent system. The only way to get to the current version is to start at the beginning and play all the way through again. So we may end up with a cache in another data store that keeps track of that current version that we can read. But if ever our business logic changes, we can restart at the beginning and reread all of the things, processing it differently. That's really helpful. Here's some examples of event sourcing system. It's great for communicating asynchronously between systems where system reliability may be a concern. On the downside, the event sourcing database needs to be all the way up all of the time, or we might have other problems. Column stores. Now, I think we don't have a bunch of time to dig into column stores, but let's just quickly introduce column stores as a little bit different than a SQL database. On the left, we have a SQL database. On the right, we have a column store. If we're trying to create a column store type index based on, say, countries in the world or provinces within the country, then we can probably index this really quickly and compress it in a really elegant way. Now, that's great for analytical workloads. We can bulk read to a particular spot. We can bulk read a lot of rows, and that works out really helpful. On the downside, it's not great for transactional workloads where we need to do a whole lot of random reads and writes. Here's some examples of column stores. Next up, let's talk about hybrid databases. So I need this, but I also need that. Or I'm stuck in a monolith, but I also need to store JSON. Hybrid databases are really good at adding a little bit of a feature of another type of database into place. If you have a monolithic database and you can't get away from it, maybe using some of the hybrid features might be helpful. Maybe I have a SQL database, but I also have a JSON column type. So now I can store NoSQL data, all of the names and values of various lookup properties where a column doesn't need to make sense. Or maybe I use time series functions within my SQL database to be able to grab event data. Grab your screenshot here, take out your phone. Here's a list of all of the data stores that we've looked at, a brief description of each one, and where it might be a best use case. Now, each data store has a best use case, but these use cases may vary. So when you're looking for a data store, find the one that exactly matches your use case. If you're not sure which data store to look at, a SQL database is probably a good default choice. We also looked at monolithic and microservice architectures. With a monolithic database, Even if we have microservices associated with our applications, then we might want to lean on a bounded context to help us practice separating our data stores. At the point where we do have enough automation to be able to provision these data stores and roll them in backup and authentication, then we can move to micro databases. A micro database is that data store owned by one particular microservice. We have a lot of different types of data stores as well. And as we get to micro databases, we can choose the data store that is specific to the need that we have. Here's some best practices. Ideally, you'll use a database as a service. This allows you to not worry about uptime and point-in-time restore. Offload that to your vendor. If you have automation, then you can move towards micro databases. Perhaps you have enough automation to be able to spin up micro databases for lots of different vendors. That's really elegant in being able to automatically enroll them in backup and authentication and keeping your micro databases clean. By default, SQL databases are a good default because you have that ACID compliance and a really fast query language. If you have an exact match for a different type of data store, or you can split this off into a separate data store in this microservice, then grab another type of data store that better matches your needs. If you don't have an exact match, maybe look for a hybrid database that does some of each, or split it into two different micro databases. This has been a lot of fun getting to show you microservices and micro databases in the microservices world. I would invite you to look beyond the monolith that you might have gotten stuck in. If you're watching this video later, hit me up on Twitter at Rob_Rich. And you can grab the slides right now on robrich.org.